Hello everyone, this is Rick from MathX, and today we're going to be taking a look at the number 25 from the F is equal to MA exam of 2023. Now, for being a test finisher, a finale for the test, this problem is actually surprisingly easy. Although there exists many really good high quality solutions out there that look at how to solve this problem using interesting topics like different reference frames or any other advanced techniques, this problem can also just be solved through a diligent application of really fundamental ideas in dynamics and kinematics. Nothing too advanced, something you'll see on like an AP Physics 1 test. So I think in this video, we're going to be going down that approach. How we could solve a test finale for the F is equal to MA exam, just using standard kinematics topics that an AP Physics 1 course, class, or just reading will teach you. So without further ado, let's just get into this problem. A skier slides from rest along a frictionless slope with an incline angle of theta equals to 30 degrees for 150 meters. Then smoothly transitions into a horizontal jumping ramp of height ht equals to 5 meters. Neglecting air resistance, after the skier leaves the ramp, how far will they travel horizontally before landing? So the first step into solving this problem is to draw a good diagram. So we already have a diagram here, but since it's a little too small for me to edit on, I'm going to take a snippet of it and expand it so we can actually draw on it and try to get a better feel for the problem. So here is our diagram. I just expanded everything that was shown here. The first thing we'll need to know in regards to how long it travels horizontally is the velocity that it enters the ramp on. So this is actually pretty standard energy utilization. So let's label this at point 1 and let's label this at point 2. We know that the potential energy here will convert to kinetic energy at point 2. So potential energy at point 1 is kinetic energy at point 2. And the potential energy at this point would be gravitational potential energy. So let's just quickly write this out, write all the steps. PE1 equals to KE2. And then PE1 would be the mass times gravity times the height. But we don't know the height, we know the length of the diagonal. However, if we just apply basic trigonometry, we know the angle here and we know the diagonal. So remember, the height of a triangle is just the diagonal times sine of the angle between. So we can call this mgd sine theta. And this will give us the potential energy at point 1. Next, we need to find the kinetic energy at point 2. Remember, the formula for kinetic energy is just 1/2 mv squared. And it also says that it smoothly transitions into the horizontal jumping ramp. The smoothly probably indicates that there is no loss of energy in between. So the energy and the speed at which it enters the ramp is also the speed at which it launches from. So we can also label this v as v0. This is the initial velocity it goes before it jumps off the ramp. So let's quickly just solve for this v0 in terms of these other variables. We just isolate the variable by first dividing both sides by m, and then multiplying 2 on the other side, and then taking the square root. So you get that v0 is equal to square root of 2g d sine theta. And in this case, sine theta is sine of 30 because the angle is 30. And we just took a parallel angle or parallel line. So here's another thing we can do. Since we have a 2 and a sine 30 which is 1/2, we can also cancel those out further. So we actually get the velocity that it launches off from as a very nice equation, square root of gd. So now we have the initial velocity it launches off. So how would we find out how far it travels horizontally? Well, remember, right? distance equals to speed times time, or distance equals velocity times time. So we can set our horizontal distance function x of t as equal to v initial times t of impact, or yeah, let's call it t final. Basically, this time is when it finally hits the ground. So we already know what the initial velocity is. If we can find out at what time, starting from here, it'll hit the ramp, we pretty much solve the problem. So now the real question is, how are we going to find out this t final? Okay, so let's just take a quick breather. This looks a little bit tricky as it is. So why don't we just pretend like the problem's simpler? Instead of jumping off the ramp and trying to land on an incline, what about if this was just a platform, right? We jump off the ramp and try to figure out the time of impact to the platform. How would we go about doing that? That is actually a much easier problem. What we would do, right, is we would figure out how much time it would take for it to fall 5 meters based on information like the gravity, and actually that's it. That's all you would do, right? In this case, to figure out the amount of time it takes from jumping off at this point onto like 5 meters below it, right? We would just set the equation, right? Our y initial would be equal to gt squared by 2. And in this case, right, our y initial would be 5, our g coefficient would be 10, to t squared, and then we would basically just solve that t would be approximately 1 second. I took g is equal to 10 here because on f is equal to ma, they use g equals to 10 instead of g equals to 9.8. To solve for the time that it takes to fall a set distance, all we would need to do, right, is just figure out the solution for t to like this quadratic equation where g is 10. However, this is not that problem, right? Because our height, our y, is not a fixed value. Sure, it initially starts at 5, but it incrementally gets larger and larger and larger. So, instead of figuring out what time the skier would fall exactly 5 meters below it, we're going to figure out what time the skier will fall, like maybe initially 5, but then 6, so on, so on. But we just want them to hit the platform, which is constantly changing in distance beneath them. And we want to figure out what time it'll hit that platform. So the best way to go about this is try to understand a function that represents the increasing distance beneath like the platform. And then using that, we're going to have to figure out what time, based on the gravitational acceleration, will he land on the platform based on like this changing y distance function. So to generate this y distance function, I just drew a largened version of like what's going on at the incline and basically how much the distance changes, like the height changes for every horizontal distance moved forward. So our total y distance, our total vertical distance for when it will hit the platform is just this length. Let's just call this y of t. And our horizontal distance traveled would be x of t. Notice that I did not include the platform, right? Because it asked for after the skier leaves the ramp. So you got to be careful about those details. So this is x of t, right? What can we see about y of t with respect to x of t, right? First, we can see that y of t, no matter what, will always have this 5 value. So we can say y of t equals to 5 plus something, right? But this something is constantly changing. But here's the thing, right? It's changing with x of t. As x of t gets bigger, the increased y of t constant will get bigger. But how do we figure out, like, how specifically? How much bigger is it getting? Well, look at, these are all right angle triangles, and we already know their angles to be 30, because that was what was given before. So, since we know one side, our x of t side, we can figure out how much the y of like the extra yt part is increasing by. And we see that this extra part, right, is increasing by like this extra height here. That is increasing with x of t. That's increasing by x of t tan 30. We pretty much get our y of t function, right, is going to be 5 plus x of t tan 30. But here's the thing, right? This is talking about how much the distance increases as the skier moves, right? But we got to remember, right? As the skier is like flying across over the incline, right? He's also falling. And just like how we wrote here, right? How we would follow a set distance in g of t squared by 2, like that's how we would represent him falling, like the distance he moves down by falling. We're going to have to also like take account for that in his y positioning, right? G of t squared by 2. So basically, his vertical like displacement at any given moment can be modeled with just these two equations, right? X of t is going to be equal to v0 times t final, or not even t final. If we want to just do a general function for like horizontal distance, it'll just be v initial times t, and his vertical displacement can be represented as y of t equals to 5 from the initial set distance of the ramp plus x of t tan 30. That's just the extra distance, like the extra height gained from moving a set distance, minus gt squared by 2. That's just the displacement from his falling. So when will he finally collide with the ramp? He'll finally collide with the ramp when this distance is 0. When this distance is 0, y of t is 0, right? He's at the ramp. He's not flying anymore. So the next step would be to solve for this equation. Solve for at which t is this distance 0. So I'm going to copy and paste this and move it over to the right. Just to finish up the algebra. Now it really just becomes an algebra mess. But it's not even that bad, right? Sure, we have our initial x of t function in solving for this equation, right? But remember, x of t is v0 of t v0 times t. And v0 we can easily compute for. Sure, we don't know what t is, right? But that still makes it a quadratic equation. We can still solve it like any other quadratic equation. So just trying to simplify this down, right? Our g will go to 10. So our t squared term will be negative 5 times t squared. Our x of t times tan 30, right, would eventually be equal to plus v0 times t. Remember, v0 itself is root g times d. So I'm just going to skip a bunch of steps. Remember, d is 150, g is 10. So our v0 would be equal to square root of 1500. And if we multiply that by t and tan 30, we're going to get our coefficient for t to be tan 30 times root 1500. So this is our coefficient for t. And then we also have the 5, right, from the initial ramp height. And this is equal to 0. Now, I know what you're thinking. What kind of garbage expression is this? And I'm going to agree with you. It's not exactly a pretty expression. But here's the thing, right? You guys are taking f is equal to ma. You're allowed simple scientific calculators. So you can just approximate values for this and then just plug it into your calculator and, you know, use the quadratic formula, right? Minus b plus minus square root of b squared minus 4ac. And doing that, you should be able to solve for t. And solving for t, right, it'll give you two values. But since we're looking at a time here, we want to take the positive value. And when you do those, you're going to get that t should be 4.686, or approximately this value, right, from just approximating the value of tan 30 times root 1500. So now we got our t impact, right? This time is when the skier will hit the ramp. But it's still not the end of the game, right? Because we need to figure out how far they travel horizontally. But now we have almost all the information we need, right? we have our v0 and we just computed for we just computed for our t final. So we can say that x, or we don't even need x of t. We can just say x, right? Our distance horizontally is equal to our initial velocity, which, as we said before, right? It's root 1500, right? Root of 10 times root 150. Times 4.686. Which, if we multiply out, once again, just plug it into your calculator, we should get that x is about 181 meters. Answer choice C. So that is how you solve the number 25 from the F is equal to ma of 2023. It was not exactly a short problem, but at the same time, right, for being a number 25, we didn't have to use any really advanced or tricky concepts to do it. All these ideas really just show up in the basics of kinematics and mechanics. So that just goes to show, right? Even the most challenging problems can just be solved with like diligent applications of really simple concepts. So I hope you enjoyed the video and stay tuned for the next MathTex upload. Thank you.